Howdy, welcome to Math 153 Elementary Statistics. I am Lance Curtis and this is the lecture for section 7.1 and 7.2. In chapter 7 we're going to look at 4 sections. First we're going to review what we've done so far and have a preview for what's ahead. So in chapters 2 and 3 we use descriptive statistics, summarize data using tools such as graphs and statistics, such as the mean and the standard deviation. These characterize distributions. Now in chapter 6, we're going to introduce the concept of critical values. So z sub alpha is what we're going to use to denote the z-score with an area of alpha to its right. So let's say, for example, that alpha is 0.025. Well, then the critical value will be z sub 0.025, which we use technology or we go old school and use the tables, we find is 1.96. So what that means is that the critical value, z sub 0.025 equals 1.96, has an area of 0.25 to the right. So here we have our critical score, or critical value rather, z-score of 1.96. This separates out the critical region from the rest of the distribution. The area under the curve to the right of that z-score, or critical value, is 2.5%. This is equal to alpha. Now, in this chapter, we're going to present what begins inferential statistics. And inferential statistics is basically concerned with 2 major activities. The first is we want to see if we can use sample data to estimate values of a population parameter. This is why the sampling methods that we've discussed earlier are so important, because we want to make sure that a sample is characteristic of the population. And if we can assure that the sample is characteristic enough of the population, then there are certain parameters in the population that we can estimate using statistics from the sample. Inferential statistics is also concerned with hypothesis testing. So we're going to make a claim about a population parameter, and then we're going to test it. That's going to be a future chapter. We won't get into that in chapter 7, but keep that on your radar because it is coming down the pike. In chapter 7, what we're going to do is introduce methods for estimating population parameters, as well as the sample sizes needed for those estimations. So we're going to look at proportions, means, and standard deviations, which, since standard deviation is the square root of variance, could also include variances. So with that established, let's get into the next section, the first section, past the review and preview, where we're going to talk about estimating population proportions. So the key concept in this section is to recognize a method for using a sample proportion to estimate the value of a population proportion. One of the main ideas we want to get across is that the sample proportion is the best point estimate of the population proportion. Okay, remember we saw earlier in chapter 6 that the sample proportion tends to target the population proportion because it is an unbiased estimator. For this reason, the sample proportion is the best point estimate of the population proportion. Now, we can use a sample proportion to construct a confidence interval that estimates the true value of the population proportion, and it's constructing that confidence interval that provides us with our estimated value for the population proportion. So it's important that we know how to interpret confidence intervals. We also need to know something about how to find the necessary sample size in order to give us that confidence interval at a given level of confidence. So to start with, let's talk about point estimates. Point estimates is simply a statistician's way of describing a single value or point that's used to approximate a population parameter. A sample proportion, p hat, is the best point estimate of the population proportion p. Again, proportions are unbiased estimators. So they tend to target the population the population parameter very well. For that reason, the sample proportion p hat is the best point estimate for the population proportion p. Here's an example. The Pew Research Center conducted a survey of 1,007 adults and found that 85% of them know what Twitter is. So the best point estimate of p, the population proportion, is the sample proportion. That means the sample proportion p hat 0.85, this is the best point estimate of the population proportion. Now this brings us to confidence intervals and confidence levels. So first let's talk about confidence intervals. Confidence intervals, which are also called interval estimates, is simply a range or interval of values used to estimate the true value of a population parameter. Sometimes they're called interval estimates, as I just mentioned, but sometimes CI is used as an abbreviation. So instead of writing out the words confidence interval, we just write CI. So sometimes you might hear me in my little jargon say CI. Just understand I'm talking about a confidence interval. A confidence level, on the other hand, is the probability 1 minus alpha that the confidence interval actually does contain the population parameter. What we're assuming with this definition is that the estimation process is repeated a large number of times. Okay, recall from the last chapter with our rolling dice experiment, we repeated that many trials. Okay, so we had 20 and we went to 100, then we went to 1,000, and we went to 10,000. Okay, we want to repeat it for a large number of times so that we get that point estimate targeting that population parameter. The degree of confidence and the confidence coefficient are other names for the confidence level. They're not as common. I've heard degree of confidence on occasion. Confidence coefficient is a hugely mathematical term. So outside of the pure mathematical circles, you will rarely hear that term. Most people that deal with confidence intervals use the term confidence level, and that's what I've heard most of the time I've run into this. Common choices for confidence levels are 90%, 95%, and 99%. These correspond with alpha levels. Okay, so if you have a confidence level of 90%, that corresponds with an alpha of 0.1. 95% confidence level corresponds with an alpha of 5%, and 99% confidence level corresponds with an alpha of 1%. How do we interpret confidence intervals? Well, there's a lot of different interpretations out there, and there's really only one right way to interpret a confidence interval. So if you go off the beaten path and get creative with your interpretation, that might lead you to make some erroneous conclusions involving your statistics. So let's make sure that we understand how to interpret confidence intervals correctly. Suppose we have the proportion confidence interval 0.828 less than p less than 0.872 based on a sample size of 1,007. What this means is that we are 95% confident that the interval from 0.828 to 0.872 actually contains the true value of the population proportion p. In other words, if we were to select many different samples of the same size, okay, simple random sampling here, so the same size, which in this case is 1,007, and we construct confidence intervals for each one of those samples that we take, okay, 95% of those intervals from those samples would actually contain the true value of the population proportion p. That's another way to look at it, okay? If you're trying to interpret a confidence interval other than what you see here, you're going off the beaten path, and you need to back step and get yourself rooted in the true way to interpret confidence intervals. Now, confidence intervals can be useful for comparing different data sets, okay? But you never want to use any overlap in confidence intervals between two different data sets when you're making formal and final conclusions about whether or not those proportions have any sense of equality to them. That's just simply not appropriate and not consistent with the proper interpretation of confidence intervals. This brings us to critical values. So, as mentioned before, we have z-scores that we call critical values. Okay? They distinguish sample statistics that are likely to occur from those that are unlikely to occur. So, here in the graphic on the right, you see we have a 90% confidence level. That 90%, 1 minus alpha. So the 90% is the area of the curve there in the center that's getting the bulk of the distribution. These are the likely values of our sample statistic. The unlikely values are in the tails. Since there are two tails to our distribution, we're splitting the alpha in half. So half of the alpha goes on the left, half of it goes on the right. Remember that the normal distribution, the standard normal distribution, are both symmetrical about the mean. The one half is the mirror image of the other. So if we take that 90% confidence level, representing the area under the curve in the center, that's the bulk of the distribution, and representing our likely values, then that means we're going to take half of what's left over, and that's what's going to be in the tails. So 5% on one side, 5% on the other. The z-scores that correspond with those boundaries, you see there, negative 1.645 and positive 1.645. Okay? These z-scores separating these tail regions, okay, and especially the right one, is what we call z sub alpha over 2, because it's a z-score, and the alpha over 2 represents the area underneath the curve that's being bounded out by that z-score. So z alpha over 2, negative z alpha over 2, okay? So typically, when you're asked to find z alpha over 2, there's no negative sign in front of it. So you're just looking for the positive value, which is the one on the right. And that's why it says there on the screen, the z-score separating each tail region, especially the right one. Because typically you're looking for the positive score. Now, z sub alpha over 2 is a critical value, because it separates z-scores from sample proportions that are likely to occur, those values in the middle of the distribution, from those that are unlikely to occur. Those are the ones in the tails. Some confidence levels that you see here, 90%, 95%, 99%, those correspond, as we saw earlier, with alpha levels of 0.1, 0.05, and 0.01. These in turn translate into z-scores, or critical values, of 1.645, 1.96, and 2.575 respectively. Now, we've seen this table before, and in showing you this table before, I mentioned that it'd be a good idea to memorize these values. If you don't memorize them, well, you'll probably end up doing it anyway, because you're going to see these numbers quite a bit. And I'm going to show you later on in this lecture where some of those frequent interactions with these critical values are going to show up. One place it shows up is in the margin of error. So when we estimate a population proportion, okay, with data from a simple random sample, there is a margin of error. Okay, so we're making an estimate. We're not exactly sure, but it's somewhere in this interval. Okay, well, that interval has with it a margin of error, because we're not really sure where in that interval it is, but it's somewhere in there. So if we could pick a value, any value randomly from that interval, it could be the population proportion, the true value, or it might not be. So there's some error associated with the estimate. That margin of error is denoted by the capital letter E. Okay, don't get confused. Okay, we're also using the capital letter E for expected value. Okay, this is not expected value. Here in this context, when we're talking about confidence intervals and confidence levels, E denotes the margin of error. We calculate E, the margin of error, with this equation that you see here on the screen. We'll go over this in a moment, but essentially you're taking a critical value and multiplying it by what is more or less a standard deviation. Now, the probability that you have that margin of error occurring is 1 minus alpha. So remember, 1 minus alpha is the same thing as your confidence level. So the higher the confidence level you have, the greater probability you're going to have that error is going to occur. Okay? Because the more sure you need to be about your answer, well, that's going to change the limits on your confidence interval. Okay? So there's definitely a relationship there. Now, the margin of error E is also called the maximum error of the estimate. That's strictly a mathematical term. Again, in all my uses of this in the real world, I have never heard the term maximum error of the estimate. So that's purely a statistician thing. But keep in mind that if you do hear that term, they're talking about margin of error. Let's talk about the margin of error equation a little bit. Make sure we understand each part and what this represents. So E, as we just got done explaining, is the margin of error. Okay? Now, on the other side of our equation, Z sub alpha over 2 is a critical value. This is the Z-score that separates likely and unlikely values, where the likely values are in the bulk of the distribution in the center. The unlikely values are in the tails. Next up, we have p hat. P hat is our sample proportion. Q hat, right next to it, is the complement of the sample proportion. So typically, in a problem statement, we'll readily identify p hat, and then we'll just subtract that from 1, and that gives us q hat. Q hat is the complement of the sample proportion. Then finally, n, on the bottom of our fraction, is the sample size. So now that we have that done, we're ready to figure out more about confidence intervals for proportions. So before we do that, though, we need to understand there's certain assumptions that are built in with the methodology for constructing confidence intervals. The first assumption we're making is that the sample is a simple random sample. This, as you've probably seen, from the previous chapters, is a common assumption that we make with our statistical procedures. The next assumption that we make is that we're meeting the conditions for the binomial distribution. So if you think back, remember chapter 5 where we talked about binomial distribution. Okay, there's a fixed number of trials. The trials are independent. There's 2 categories of outcomes, success and failure, and the probabilities remain constant for each trial. Okay, probabilities of success and failure. The last assumption that we're going to make is that there are at least 5 successes and 5 failures. Okay, this assumption is important because it allows us to use the normal distribution as an approximation for the binomial. And using the normal distribution then unlocks all of the tools that we've discussed in the previous chapter, chapter 6, about the normal distribution. So, with those assumptions met, there are different ways that we can actually express confidence intervals. Okay, statisticians, pure mathematicians, they like this way: p hat minus e less than p hat plus e. Okay, where e is that margin of error that we saw previously. Sometimes in some quarters, I like to shorten that a little bit. So they tend to just take the limits of the confidence interval and write it in parentheses separated by a comma as though the limits were an ordered pair. And it's not a bad way to think about it. I mean, you've got a lower limit, you've got an upper limit. So there's nothing wrong with expressing it as an ordered pair. Of course, if space is really tight, and in some quarters the convention is just to do this anyway, then you just press p hat plus or minus e, and you let somebody else do the math. Seeing as I'm a lazy engineer, you can probably guess that this last format is my favorite. Because, yeah, I have to calculate e, I have to get my point estimate. Don't ask me to actually add and subtract numbers together. You have access to a calculator. You can do that pretty well on your own. So yeah, the last format there is my favorite. But, whatever, your homework problem is asking you for, that's the format you need to use. Now, a common convention, no matter what format you use, is to round your confidence interval limits to 3 significant digits. So, with all that said now, how do we actually go about constructing the confidence interval? Well, the first step is to verify that the required assumptions have been satisfied. So the sample must be a simple random sample, the conditions for the binomial distribution must be met, and we must have at least 5 failures and 5 successes, because that allows us to use the normal distribution to approximate the distribution of sample proportions, which, if the conditions for the binomial distribution are met, is very likely a binomial distribution. Now, the second step is to find the critical value, z sub alpha over 2, okay, that corresponds with whatever confidence level we pick. 90%, 95%, 99%, whatever it is, there's an associated critical value with that, and we need to calculate that. Then we need to calculate the margin of error, okay, which of course uses the critical value, but then we use that to calculate the margin of error, and then once we have the margin of error, then we can find the values of our lower and upper limit for our interval, and then we place them in the general format for the confidence interval. Whichever format it is that's conventional for us to use, that's the one we're going to pick. And finally, we want to round the resulting confidence interval to 3 significant digits. This, again, is a very common convention. So let's look at an example. Pew Research Center poll of 1,007 randomly selected adults reports 85% of respondents know what Twitter is. So we're already from this statement, just this one statement, we know our sample size is 1,007. We also know that our population proportion, our sample proportion, that's p hat, is 0.85, 85%. Okay? Once we know what p hat is, then by deduction we know what q hat is. We just subtract it from 1, and that gives us 0.15. Because remember, q hat is the complement of p hat. So now that we know 3 of the variables that we need for, performing a confidence interval, let's answer the following questions. 1. What is the margin of error E that corresponds to a 95% confidence level? Second, what is the 95% confidence interval estimate of the population proportion P? And 3, based on these results, can we safely conclude that more than 75% of adults know what Twitter is? And then finally, how can we briefly but accurately describe the results and include all of the relevant information? So let's tackle the first question first. What is the margin of error E that corresponds to a 95% confidence level? Well, first, we need to make sure that our assumptions have been satisfied. Okay, remember that all of our methodology for constructing confidence intervals are based on certain assumptions. So let's check them out. First, do we have simple random sampling? Well, in this case, yes, we do. Do we have a fixed number of trials? Yes. The fixed number of trials we have is 1,007. Are the trials independent? Yes, the trials are independent. Okay? The answer from any one individual is not dependent upon how anyone else answered. So yes, the trials are independent. Are there only 2 outcomes per trial? Well, yeah, either you know what Twitter is or you don't. So there's only 2 ways it can go. Is the probability of success consistent with each trial? Yeah, it's pretty consistent. Do we have at least 5 successes and 5 failures? Yeah, we've got 856 successes and 151 failures. And you can see I get those numbers by using the proportions from my sample for quote-unquote success and quote-unquote failure. So yes, we've met that. We've met all of our assumptions. They are all satisfied. Now that our assumptions have been satisfied, we can just use our margin of error equation. So here's our equation. Plug in what we have. Our critical value of 1.96. P hat is 85%, which means Q hat is 15%. Our sample size is 1,007. Punch this out on your calculator, and out comes the marvelous 0.0221. Notice that this is the margin of error E that is rounded to 3 significant figures. Second question, what is the 95% confidence interval estimate of the population proportion P? Well, first, we need to find our point estimate for the population proportion. Okay? So, does the sample proportion target the population proportion? We're asking this question because we're looking for the point estimate. We want something that targets the population proportion. Okay, so the first thing you're going to think of is the sample proportion. So does the sample proportion target the population proportion? The answer is yes, it does target it because, remember, proportion is an unbiased estimator. So because the sample proportion targets the population proportion, the sample proportion is our point estimate. This is what we're going to use to estimate the population proportion. So P equals P hat, which, as we saw, was 0.85. Now, we substitute the given values into our desired general format. So here's our format, P hat minus E, less than P hat plus E. And we substitute in what we know. So P hat is 0.85, our margin of error, 0.0221. And we see we're subtracting it on the left to get the lower limit, adding it on the right to get the upper limit. And out comes 0.828 less than P less than 0.872. This then is our confidence interval, 95% confidence level. And again, note how we rounded our limits to 3 significant figures. Question 3. Based on these results, can we safely conclude that more than 75% of adults know what Twitter is? Well, what we're really asking here is this question. Is the true population proportion greater than 75%? We don't know what the population proportion is, but we have a confidence interval, and we're 95% certain that that true value is somewhere in that interval. So what we're really asking when we ask, can we safely conclude that more than 75% of adults know what Twitter is that true population proportion value more than 75%? Well, look at your 95% confidence interval. 0.828 less than P less than 0.872. What this confidence interval says, remember the proper way to interpret confidence interval. We're 95% confident that the true population proportion is somewhere between 0.828 and 0.872. So all the values that we have inside that 95% confidence interval are greater than 0.75. So yes, it is safe to conclude that more than 75% of adults know what Twitter is. Now another way to look at this is to think of confidence intervals in terms of a number line. So if we draw a number line and we put then our confidence intervals, the lower limit of 0.828 and the upper limit of 0.872 on the number line, it may look something like this. What we're saying with the confidence interval is that we're 95% certain that in the shaded region between the upper and lower limits of our confidence interval, we're 95% certain that the true population proportion value is somewhere in that shaded region. So then when we're asked, can we safely conclude that more than 75% of adults know what Twitter is? Well, 75% on the number line is over on the far left. And as we can see, all the values in the shaded region that we're 95% certain it's somewhere in that shaded region, that entire shaded region is well to the right of 0.75. So then we can conclude, yes, it's safe to conclude more than 75% of adults know what Twitter is. Fourth question, how can we briefly but accurately describe the results and include all the relevant information? Well, you're asked to write, and when you're writing, I mean, there's often many different ways to achieve the same end, but here are a couple of possibilities. 85% of adults know what Twitter is. That percentage is based on a Pew Research Center poll of 1,007 randomly selected adults. In theory, in 95% of such polls, the percentage should differ by no more than 2.2 percentage points in either direction from the percentage that would be found by interviewing all adults in the United States. Clearly, this was written by a statistician. So me, the engineer and also the writer, looks at this and says, wow, that's really wordy. Can we cut that down a little bit? Because if you can say the same thing with fewer words, it tends to communicate your message more powerfully. Here's what I came up with. According to a Pew Research Center poll of 1,007 randomly selected adults, 85% of adults know what Twitter is. The 95% confidence interval margin of error for that statistic is 2.2 percentage points. It says exactly the same thing as the first, but it's much more succinct, kind of easier to understand, and it's certainly more powerful. Now, there are many other ways to do this, okay? But keep in mind that however you go about this, you need to make sure that two pieces of information are provided. You need to provide the confidence level, and you need to provide the sample size. And when you think about statistics that are reported in the media, it's often that you find the sample size reported. Sometimes you don't, but often you do. However, the confidence level is almost never reported, and yet it's a vital piece of information when you're reporting a statistic. So when you report your statistics, especially when you're talking about confidence intervals, you need to make sure you provide those two pieces of information. Now, on a side note, since we are talking about a poll result here, it's very common to look at the size of the sample in relation to the size of the population. And if that ratio is small enough, then it's common to conclude that the poll results are somehow flawed, that they're not up to snuff, that they don't have good quality. And that's really not the case. The quality of poll results depends much, much more on the sampling method and the overall sample size itself, irrespective of the size of the population. So population size doesn't really play into it. It's the size of the sample itself. That's what we need to focus in on. Well, that of course begs the question, how big of a sample do we need to have in order to estimate the population parameter? I mean, how big is big enough? Well, we can find out. All we have to do is just take that margin of error equation that has a sample size as a variable, and we solve for that variable. So let's start out with our margin of error equation. Here we have it here on the screen. And the first thing I'm going to do is divide both sides by my critical value. This moves it over to the left, as you see here. Next, I'm going to take the reciprocal of both sides. This basically flips everything over. So what's on bottom goes on top, what's on top goes on bottom. Now I'm going to get rid of my radical sign by squaring both sides. That gets rid of my radical sign. And now both sides squared, I'm going to divide both sides, multiply both sides by p hat q hat. This brings it over from the right side to the left side of my equation. Notice how I also resolved the squared term. I have z squared on top and e squared on the bottom. Now I've got n all by itself. So I've solved for n. But it's customary to take the variable that we've solved for and stick it on the left side. So I'm just going to swap sides here in my equation. And here we have final sample size equation, n equals p hat q hat, z sub alpha over 2 squared divided by e squared. Now we don't always know what p hat is, and if that's the case, then we just substitute 0.25 in for p hat q hat. That reduces our equation to 0.25 z squared over e squared. Where does the 0.25 come from? Well, if we don't know what p hat is, the most likely estimate for p hat is going to be 50%. Because of all the different proportions that we could have, the one that shows up most frequently is 1/2. So if p hat is 1/2, then that means q hat, the complement of p hat, is also 1/2. Because 1 minus 1/2 is 1/2. Then when I take 1/2 and multiply it by 1/2 to get p hat times q hat, 1/2 times 1/2 is 1/4. 1/4 is 0.25. So that's where the 0.25 comes from. Either way you look at it, you always want to round up to the next largest whole number. Sample size is a discrete data quantity. So we want to make sure that's a whole number. We don't count parts with discrete data. We only count whole numbers. So you always want to round up. And it's very rare for you to actually calculate the sample size with this equation and come out with a whole number. You're going to get a decimal. So when you get that decimal, just round up to the next largest whole number, and you're done. Let's look at an example involving online clothing sales. There are many companies that are interested in knowing the percentage of adults who buy clothing online. Here's a question. How many adults must be surveyed in order to be 95% confident that the sample percentage is an error by no more than 3 percentage points? First, we're going to answer this question by using a recent U.S. Census Bureau statistic that says 66% of adults buy clothing online. Then we're going to answer the same question again, but without any prior knowledge of a possible value of the proportion. We'll show you how to work it both ways. So, working it the first way, part A, 66% of adults buy clothing online. The first thing we want to do is identify the variables from our equation in the problem statement. So first, let's look for p hat. P hat is going to be 0.66. Why 0.66? Because 66% of adults buy clothing online. This is the proportion of those that we're surveying who actually buy clothing online, the quote-unquote success. Well, if we know that p hat is 0.66, then that leads us to calculate q hat. Remember, q hat is the complement of p hat, so we subtract it from 1, and out comes q hat, 0.34. Now, our alpha level is 0.05. Where did the 0.05 come from? Well, alpha is 1 minus the confidence level. And in the problem statement, we said we wanted to be 95% confident. So that means we take 1 minus 0.95, and that gives us the 5%, or 0.05. That then leads us to calculate our critical value, z sub alpha over 2, which turns out to be z sub 0.025. And when we go to calculate that critical value, we find it is 1.96. The margin of error for this particular problem is 0.03. Where did that come from? Well, in the problem statement, it reads we want to be in error by no more than 3 percentage points. So 3 percentage points, 3%, 0.03. Now that we've got our variables, the next thing we want to do is substitute into our sample size equation and then solve. So here's our sample size equation. We substitute in what we know. So p hat is 0.66, q hat 0.34, our z-score critical value 1.96. We're going to square that. And then down below, our margin of error 0.03, which we also square. Punch this out on your calculator, and out pops 957.84, which of course would round up to the next whole number to get 958. This then is our sample size. And what this means is to be 95% confident that our sample percentage is within 3 percentage points of the true percentage for all adults, we should obtain a simple random sample of 958 adults. Now, what if we didn't have that statistic from the Census Bureau? We don't have any prior knowledge of a possible value of the proportion. Well, we can still solve the problem with the estimate that we learned earlier. First, identify your variables from the problem statement. And we don't know what p hat is. Okay, we don't have a statistic to rely on here. So if we don't have p hat, because we don't have the knowledge of any possible value, then how do we get q hat? Well, remember what I showed you earlier. We can estimate the product of p hat q hat with 0.25. That's what we're going to do in this case. Our alpha didn't change. It's still 0.05 because, again, we still want to be 95% confident. So that leads us to the same z-score critical value, 1.96. And our margin of error did not change because, again, we want to be in error by no more than 3 percentage points. So now we have our variables. Go ahead and substitute what we have into our equation and solve. So here's our sample size equation. We substitute in what we have, punch this out, and we get 1,067.11, which rounds up to 1,068. To be 95% confident that our sample percentage is within 3 percentage points of the true percentage for all adults, we should obtain a simple random sample of 1,068 adults. Notice how this is a little bit higher since we used that estimate of 0.25 for p hat q hat. That's what we would expect, okay? We don't know what the value is, so we would expect our estimate to give us a result that's a little bit higher, okay, to fudge in the error from using an estimate for p hat q hat. That leads us to the end of this lecture. If you have any questions, you know how to get a hold of me. Otherwise, I will see you in class. Thanks for watching.